Hello everyone, welcome again in Eng-Man YouTube channel. Today we will learn about how to design gas lift in Pipesim software. We are now in Pipesim software. In the last two videos regarding gas lift, we have learned about deepest injection point and gas lift response. And today we will discuss about gas lift design. And in the next video, we will talk about gas lift diagnostics. All right. So it's going to be very interesting. I hope the video is useful for you. Okay. First, general, well name, gas lift well, active, yes, well type production, check valve setting, block reverse, comments, gas lift well in pipe sim. All right. Now tubulars, set up first casing at depth of 12,000 feet. Let's open the catalog. I want my casing to have outer diameter of 7 inch. So type in 7 inch and I'm going to select this one, right? Click OK. Okay, I have set up my casing and then of course my tubing. It has been created automatically. I will set the bottom of my tubing at depth of 11,500 feet with inner diameter of 2.992 and wall thickness of 0.254 with devolved roughness. All right, I've set up my casing and tubing. Mode simple, dimension option, wall thickness. And then we go to deviation survey. We will choose or we will construct a vertical well in this example. Depth reference original RKB, wellhead depth of 0, bottom depth of course 11,000. And we will have packer in this case. We will locate our packer at depth of 11,300 feet. All right, this is our packer. And then for artificial lift, leave it as it is, but later on we will install gas lift. For heat transfer, we leave it as it is. And then of course, completions. We add a completion, geometry, vertical, fluid entry, single point. We will locate our middle perforation at depth of 11,800 feet. Type, of course, perforation. And for the IPR model, we select well PI. All right, now you can see our perforation is located down here. And this is the picture or icon of our flow. We will have tubing flow. All right. And then let's input the reservoir data. Reservoir pressure of 3,100 psia. Reservoir temperature of 200 degrees Fahrenheit. IPR basis, of course, liquid. Productivity index of 6.1. Make sure you check use Vogel below bubble point. All right. Send, leave it as it is. Of course, we will input our fluid model. Click new. Okay. All right. We will name our oil with water cut of 10%, GOR of 450, standard cubic feet per stock tank barrel, gas specific gravity of 0.75, water specific gravity of 1.02, and API gravity of 30-degree API. We don't have any impurities. All right. Okay. And go back to reservoir. We have our IPR right now. All right. Okay. First, let's see if we run nodal analysis. Select location, bottom hole. and outlet pressure or wellhead pressure of 250 psi. No sensitivity at this point. Run. All right. You can see there is no intersection between our IPR and VLP. So we cannot flow in this situation. And in this case, we will install gas lift. In the previous two videos, we have learned about gas lift response, where we determine that our optimum injection rate is 3 million standard cubic feet per day. All right. And we have determined also the optimum injection point. So at this point, we can go directly to gas lift design. All right. This is our gas lift design window. It's going to be very, very interesting. Let's check them one by one. We start from boundary conditions, branch end, gas lift, wellhead, of course. And for the calculated variable, we will calculate our production rate, production outlet pressure, 250 psi. And you can see the box that have been highlighted by red color. In these boxes, we need to input our information. So as you can see in unloading outlet pressure, there is no red highlight, so we can leave it blank, right? And reservoir pressure, of course, 3,100. Reservoir temperature, 200 with input GOR and water cut, as you can see. And now injection parameters. We have our operating injection pressure of 2,100 psia. No need to input our kickoff pressure with surface injection temperature of 90 degrees and target injection rate of 3 million standard cubic feet per day. So you can go back to watch my video about gas lift response. And there you can see that we select our target injection rate to be 3 million standard cubic feet per day as our optimum injection rate. All right. Gas specific gravity, 0.64. And then for the calculation options, production pressure curve, okay. Production pressure model, injection gradient will include our friction losses, right? To be more accurate, top valve unload temperature, injection, all right? Lower valves unload temperature, also injection. Minimum unloading liquid rate, you can leave it as it is. The default value is 500 stock tank barrel per day. Now we go to spacing control. Design spacing, of course, we select new spacing as we don't have any spacing in our well configuration. Design spacing method, IPO, surface close, right? And top valve location, we'll assume liquid to surface because you see, we usually design our gas lift to accommodate completion activity. So usually after the completion or after well service, after workover, we usually have completion fluid inside our annulus, and usually the liquid fill the annulus up to the top or the surface point. So let's assume liquid to surface. You can also specify liquid level if you are certain about where is the depth of your liquid level, or you can also use calculated liquid level. In this case, assume liquid to surface, maximum injection TVD, of course, at this point, close to our packer, right? We also can enable bracketing, unloading gradient. You can use this number. This is usually the gradient of our completion fluid. It is, of course, heavier than water. That's why the liquid gradient is 0.465 psi per foot. All right. And minimum valve injection pressure drop. In this case, the default value is 150 psia. It will ensure a stable injection. And also For the minimum valve spacing, you can use this default number, or you can also input your number at this box. For design bias, we can leave it as it is as per default. For surface close pressure drop, 15 psia, and locating pressure drop at valve location, 50 psi. Okay, they are good numbers. Transfer factor options, we can select percent difference between production pressure and injection pressure. All right, transfer factor 0. Adjust operating valve PTRO 0 also. And to ensure a stable injection operation, we will select orifice as our gas lift operating valve. So we check this one. All right. Also for the valve temperature correction, we can leave it as it is. For test rack temperature, nitrogen temperature corrections, we can leave it as it is. And lastly, for valve selection filter, manufacturer will select SLB Chemco with valve type of IPO, valve size of 1.5 inch, valve series of R20, right? And minimum port size of 0.125 inch and valve orifice series of RDO. All right, so far so good. And of course, at this point, we can run and see the results. All right, the design is completed, right? This is our gas lift design configuration. All right, this one is pressure line, this light blue line. Okay, pressure inside our tubing, of course. And this one, casing gas pressure. And this orange line is, of course, our temperature. We can know also our liquid level pressure, gradient lines, and valves opening pressure, valve closing pressure. We can see here the green circle or the red circle, right? Transfer point. And this black dashed line indicates our valve. So we have our valve here, 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 right? All right. You can also show grid, right? You can see the series of your valve, the type, and the injection pressure, the production pressure inside the tubing, right? Injection flow rate for the gas lift injection flow rate, and the unloading rate for our liquid. Go back again to show plot. All right. Yeah, you can see our wellhead pressure, of course, 250 psia as per design. This is the axis for pressure. Go up. This is our wellhead pressure. Okay. If you are not satisfied enough, you can click this one to enable redesign. Let's check enable redesign, and we will go back to gas lift design automatically so that we can do the redesign. Whether we want to do redesign for the depth, temperature, and or for the valve. Okay, let's go back to design results. You can also click this one, view data in the table. You can copy everything and paste on your spreadsheet. Okay, show grid. All right, it's very interesting. And you can see our casing head pressure, of course, 2100 psia, and total injection gas rate, of course, as per input, 3 million standard cubic feet per day. And this is important, the resulting liquid flow rate at outlet. So now we can flow at flow rate of 4,700 stock tank barrel per day. And this is our injection point, deepest injection point, DIP. We will locate our injection point at 10,320 feet. And this is, of course, our reservoir pressure. If we agree with this design, we can click this one, install design, and then close. Now you can see our well has been updated or upgraded or equipped with gas lift, right? You can see. And this is the table for our gas lift valves in gas lift section. This is the gas properties, gas specific gravity, and also the information for the gas lift system, injection gas surface condition, target injection rate of 3 million standard cubic feet per day, and surface injection pressure of 2100 psia, surface injection temperature of 90, right, with minimum valve injection pressure drop of 150 psi, and this is valve performance data, right? So when we talk about gas lift design, we actually are talking about this table. So in our example here, we have 5 gas lift valves, right? And our operating gas lift will be at the 5th valve, RDO, this one. All right. And you can see this is the setting depth of each gas lift. And our operating valve will be located at 10,147 feet. You can see the series of the valves here. For valve number 1 through valve number 4, the series is R20. And for our orifice, the series is RDO. You can see here, valve 1, 2, 3, 4, the valve type is IPO. Whereas for the operating valve, the 5th valve, we will use orifice. All right, this is the port size and PTRO, the pressure of test rack opening. All right, this is the discharge coefficient. All right, and also we need to input the data here. You can see here, fixed injection ports. Right now we are still in injection valve system. We go to fixed injection ports. All right. At this table, we need to input our injection quantity, the gas injection rate. We need to input our data here in order to be able to do nodal analysis. So let me show you. If we haven't input the data here, we cannot actually do nodal analysis. We go to nodal analysis. All right. You can see here, we cannot run nodal analysis. That's why we close and we need to input the data in this table. To make it simple, we will enable this for gas lift valves because in normal operation, we will inject only through the 5th valve, which is the orifice. All right. As you can see, if we inject at deeper location for our gas lift system, we will achieve more stable or more efficient production. So we prefer injecting our gas at deeper location. In this case, we will inject our gas at this level. So we can input our data here. Injection quantity, 3 million standard cubic feet per day. You can see injection basis is injection gas rate, but we can also select set GLR or increase GLR by some number. Okay, so far so good. So we can enable valve number 1, 2, 3, 4 and only activate the 5th valve. All right, now we go to nodal analysis. All right, first we run the nodal analysis without sensitivity. You can see We can do nodal analysis right now. The outlet pressure still 250 psia. Run. All right. You can see we can flow because we already equip our well with gas lift. Previously, we cannot flow. All right. You can see the operating flow rate is 4,626 stock tank barrel per day with flowing bottom hole pressure of this value. The intersection is at this point, right? You can see our maximum flow rate actually is quite high, and we can only achieve relatively low production rate even with gas lift. All right, so if you want to improve your production rate, maybe you can select electrical submersible pump rather than gas lift. All right, but what important now is actually we can flow because of the gas lift. All right, so far so good. You can also check the profile results, right? You can see there is a change of gradient around this location, around the depth of 10,000. Why? Because we locate our gas injection here. We have our gas leak valve here. So we can see a change of flow gradient or liquid gradient because of gas entering the tubing and mixing with the reservoir liquid, the production fluid. All right, so far so good. You can also see the grid, right? You can copy the table and paste on your spreadsheet. You can also view the data here in the table. All right, now let's see, we want to do sensitivity analysis for the outflow. We go to this one. Now we will do sensitivity for injection gas rate. We start by 0 in the case of we don't equip our well with gas lift, and we try 1, 2, 3, 5, and 10. Run. It's very interesting, right? Now, first you can see with 0 injection rate, or in other words, without gas lift, we cannot flow. This one, 0 injection rate. This one is the outflow. And you can see on the table, unconverged, because we don't have injection in our case for the first case. All right, and you can see also with the increasing gas injection rate, we can achieve higher production. But actually, if we inject too much, let's say if we inject 10 million standard cubic feet per day, we actually produce at lower production rate from 4,800 go down to only 4,500 if we inject excessively. All right, so it's very interesting. Let's recap. In this video, we have learned about designing a gas lift. In previous 2 videos, we have learned about gas lift response and deepest injection point. In this video, we have learned about gas lift design. Okay, we proved that after we equip our well with gas lift, we can actually make our well from dead condition, cannot flow, to producing condition. All right, in the next video, we will talk about gas lift diagnostics. This is also a very important section. So see you in the next video. Thank you.